So now we are going to start with the electronic configuration first, because that forms the basis of all properties. So if we talk about electronic configuration, so you all know that if we talk about atom, we have the nucleus, right, a positively charged nucleus, and there is an electron cloud that is made up of a negative charge which spread around the nucleus actually. So here we are going to fill the electrons in the different shells. As you all know that in a shell we have the subshell, right? In a subshell we have the orbital. Right. So we are going to fill the electrons in the particular shell, taking into consideration the subshell and the orbitals. So if we talk about the electronic configuration, so you have done in the atomic structure, you all know that the rule for filling the shells is given by strictly according to the Halfbow Principle, Pauli's exclusive principle, and Hund's rule of maximum multiplicity. So according to Halfbow Principle, it is stated that the electrons are actually filled in the shell, right, in this order. You all know that. You have done in +1 as well, according to the increasing energy. That means the orbital which has the lower energy is filled first, and then we go on filling the orbitals which have more energy. So that means the filling of orbitals is from the lower energy, and we go on filling up to the orbitals with the increasing energies. So now if you take into the consideration, so that is the D block electronic configuration. So before we take into consideration that, I want that you should know actually that what the term penultimate and anti-penultimate shell means, because we will be using these terms very often in this chapter. So see, if I talk about this, if I talk about the shells, so you know that my final shell, suppose I see this case, right. So if I talk about my final shell, so obviously this 3-1 is my final shell, this is my final shell, that is my valence shell. The shell which is inner to this, that is this 2s and 2p, the shell which is inner to the outer shell is called as penultimate shell, and it is indicated by n-1. And the shell which is present inner to the penultimate is the anti-penultimate shell, and it is indicated by n-2. So it's very simple. See, if you have the shells, so you have arranged in the increasing order of energies. So the last shell is called as the final shell, that is the valence shell. Inner to that is the penultimate shell, and inner to the penultimate shell is the anti-penultimate shell. So if somebody asks you that if I am talking about the fourth shell, and fourth shell is my valence shell, and I ask you that which shell is going to be my penultimate shell. So obviously what you will do, you will take the n value of the valence shell, that is the 4, as I told you. So just subtract 1, so it is 3. So that means your penultimate shell is the third one. And if I ask you about anti-penultimate shell, then from the valence shell just subtract the 2. So that means if you minus 2 from 4th, that means 2. So that means your anti-penultimate shell is the 2-1. So 4th is my final shell, 3 is my penultimate shell, and 2 is my anti-penultimate shell, right. So actually the anti-penultimate shell is the innermost, and after that we have the penultimate, and after that the outer one is called as the valence shell, right, because you will be using these terms. They actually play a very important role in D and F block. So now coming on to the the configuration first. So like the general electronic configuration for this, as we know that filling of the d orbital is going to take place. So if I ask you about the general electronic configuration, obviously it is going to be this one, that means the final shell, right, and this is the penultimate shell. So that means in penultimate shell, that is n-1d, the electrons can be 1 to 10, and the outermost shell, that is the ns, the electron can be 1 or 2 or it can be 0 also. It can be 0, 1 to 2. So but if we see in this case, this D block strictly, ns is 1 to 2. Right, but still we will see certain exceptions, because when we are filling the electrons, we need to concentrate on the stability as well. So sometimes in certain cases we will encounter certain questions where we need to just violate the Halfbow principle. We have to go against the Halfbow principles, a slight you can say the difference with the Halfbow rule, that is that instead of filling a complete shell first, we will be filling the other one, and the reason totally behind that is the energy factor and the stability factor. So just look at the examples first, you will be well versed at what I am trying to tell you. So in the first period, if I talk about the the configuration, so in this case the filling of a 3D orbital take place, that will be the anti-penultimate shell. Sorry, that will be the penultimate shell. So my valence shell is obviously going to be 4s. So in the first period, the filling of 3D and 4s will be done. So let's write the configuration for scandium. So it is argon 18, 3D1, 4s2. If we talk about the 22 one, the element with 22 atomic number, argon 18, 3D2, 4s2, right. Coming on to chromium, you all know that copper and chromium have anomalous configuration actually. The reason behind the more energy exchange and the half filled and fully filled orbitals are more stable. So that means if we talk about the energy exchange or the fully or half filled orbitals, we are talking about the stability on the whole, right. So that means if we write the configuration for chromium, it should be like this. But instead of this, what is there? Actually there is a slight difference of energy between 3D and 4s. But if we move one electron from 4s to 3D, that if we write it as 3d5, 4s1, 3D will be half filled, and we know that half filled and fully filled orbitals are more stable. So everything in the universe needs the stability. So that is why it is just a matter of shuffling of electron between two orbitals which have slight difference in energy. So that means this electronic configuration is like this. So in the fifth period, we know that there are the elements ranging from 39 to 48. So let's take an example of 39, that is yttrium. So we have configuration as krypton 4d1, 5s2, zirconium 40, krypton 36, 4d2, 5s2, niobium 41, krypton 36, 4d3, 5s2. Here again there is an exception we will get to see, that means this actually will violate the Halfbow principle. Here also there is a slight difference of energy between 4d and 5s. So what happened, actually when you fill the electron in 5s, like when you add the electron, like you have been filling the electrons first into s and then into d, you know that. So when we enter one electron, when we add one electron to 5s, it is actually stable. But when we add the two electrons, the energy of 5s increases to an extent that it makes the configuration or the element unstable. So at that time one electron from 5s just jumps into 4d and the configuration becomes 5s1, 4d4. The reason behind that is only because it corresponds to the stability, because few elements, when the electrons are added, their energy actually exceptionally increase in certain case, and to lower that value of energy or to impart stability, we need to shuffle the electrons, and we can do it only between the orbitals which have slightly difference in the energy. Similarly, when we talk about palladium, it is 46, it is krypton 36, 4d9, 5s1, it should be like that. But as you can see that if we will shuffle the electron, if we will shift the electron from 5s to 4d, it will become 4d10 and 5s0. So that means this configuration can actually make the element stable, because again 4d has completely filled electrons, that means it is imparting a stability to an element, because we know that completely filled, fully filled or half filled orbitals are more stable. Similarly, in molybdenum 42, we have krypton 36, 5s2, 4d4. But in the same way, if we move the electron from 5s to 4d, it will become 4d5 and 5s1. Again it becomes half filled, and we know that half filled and fully filled orbitals make the atom actually stable. Right. So these are the few exceptions, but when somebody asks you about general configuration, you don't need to write the exceptions actually. You need to write the general configuration, but you have to sidewise remember the exceptions also, because if you get a configuration of molybdenum, you should know that we have just did the shuffling in order to impart the stability. The configuration is not this, the configuration is strictly obeyed as this, that is the 4d5, 5s1. So whenever you are filling the orbitals, keep into mind that whenever you get to see that by just moving a one electron from one orbital to another with slight difference of energy imparts the stability. So don't think, just do that, right, because that will be a correct configuration. Now, coming on to the third, the fourth, fifth and sixth period, the lanthanum, that is 57. The configuration is xenon 54, 6s2, 4f and 5d. So, we have to fill actually 4f and 5d. So, 54 plus 2, 56, and we need to make 57. That means 1 electron more. So, what happens in this case, we have like although we have to add into 4f, because if we look for the increasing order of energy, 4f has to be filled first, but in this case we are not filling 4f, actually we are filling the 5d, because 4f and 5d actually they have nearly same energies, but in this case in lanthanum the 4f energy is actually risen up to certain level as compared to 5d. So, instead of adding electron into 4f, we add into 5d orbital. So, the configuration is actually this thing. So, because there is no electron in the f orbital, so that is the reason that lanthanum is placed here, and after that, that is from extending from the 58th atomic number, it is the F block element. So, if somebody asks you that lanthanum is a F block element, strictly you are going to say no, it is not an F block element, because here the F block has no electron in it, right. And but after lanthanum, that is extending from 58 to 71, all are F block elements. Similarly, in actinium we will be seeing that here again the 4f, the electron does not enter into the F orbital, that is the 5f orbital. Instead of that, we will see a same kind of configuration there, and after that actinium, that is from atomic number 90 to 103, all will be F block, because electrons will be entering into the F block, as the F block will have the less energy as compared to the d orbital, right. So, this is what is the electronic configuration. One more thing, one more thing I just want to I will do with an example. Suppose I ask you that tell me that zinc is a d orbital element or not, right. So, as the definition suggests, any element which has unpaired electron in d orbital, or you can say which have incomplete filled d orbital, or in its ground state, or in any other oxidation state. Like if you are considering that d orbital should be incompletely filled, it is not only in a ground state, you can also consider in any oxidation state. So, that means in zinc case, we can consider zinc, and even we can consider Zn2 positive. So, if we write the configuration for zinc, so obviously you know that it is already being written, that it is this thing, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. This is the configuration for zinc. So, as you can see in this one, that d orbital is completely filled, and you know that when d orbital is completely filled, it is not regarded as a d block element, right. So, let us see for Zn2 positive now. If we are seeing for Zn2 positive, that means we need to remove 2 electrons, right. So, I am just removing from this 4s orbital, because we can remove only from the valence shell, and as we know that 4s is a valence shell, so we are removing 2 electrons from there. So, again what is the configuration? Again we are left with 3d10. So, I can write this thing, argon 18 and 3d10, again completely filled. So, that means it is not occurring as it is not having an incomplete d orbital in ground state, or if we talk about in any other oxidation state, and that is the reason that it is not considered as d block element. Similarly, take an example, we will take an example for copper also. We know that the copper has an anomalous configuration, that is argon 18, 3d10, 4s1. Right. So, this is the ground state configuration actually. So, here you can see that the d orbital has completely filled, it is completely filled. So, that means as per definition, it should not be regarded as a d orbital element, right. Let us see for any other oxidation state, let us say for Cu positive. So, when we talk about Cu positive, it is 3d10 and 4s0. Again d orbital is completely filled. So, that means it is not a d orbital element. Again we have one more option left, because the copper shows a valency of cuprous and cupric. So, that means we can also look for the d orbital in the Cu2 positive as well. So, just let us write for Cu2 positive. It is argon 18, 3d10, 4s1. It was the ground state. Now, I need to remove 2 electrons. So, one I will be taking off from here and one from this case. So, that means I am left with 3d9. So, here we can see that it has incompletely filled d orbital. So, that is the reason that copper is regarded as a d block element. So like if somebody asks you about that whether it belongs to, it is a d block element or not, so how you are going to prove it? Just look at its ground state configuration and just look at its any other oxidation state. So if in any of the case you found that the orbital is incompletely filled, so that means definitely it is going to be it is called as a d block element, right? Placing in the d orbital doesn't mean that it is a d block element, because we need to satisfy the definition as well. That means it should possess the incomplete filled d orbital and in ground state or in any other oxidation state, right? So if if we talk about zinc, cadmium and mercury, they are not d block elements if we consider their electronic configuration, but if we consider their properties, actually they are d block elements because they have properties similar to the metalloids. That is the reason they are placed among d block elements, right? So now we are starting with another property. I think electronic configuration concept is clear. Keep in mind that whenever you are writing the configuration, don't get confused. You cannot learn these things actually, but whenever you are doing a configuration, just look for the stability as well, because every element, everything in the universe, not even the element, everything in the universe just running behind the stability, right? So why not elements? So as you can see that they have a d orbital with 4 electrons and 5s with 2 electrons. So obviously it is just one step away from the stability. So the electron will move from that shell to the other shell, which imparts the stability. So just concentrate on that whenever you are attempting the electronic configuration.